So I'm very glad to be here talking in front of you today about the energy management optimization in smart grids. So this talk is the first talk of, well, two talks. The first one, also happening here today, will be a more general talk discussing several topics. And the second one will be more focused on decentralized smart charging. I will also talk about decentralized smart charging today, but I will focus more on in the second talk that will be in Energyville in 2 days on this particular aspect and describing more the theory behind adaptive multi-agent systems and bandit theory. So I will maybe give you a hint about these different tools in this presentation, but that will be a very short summary. So that's the plan for today. First, I will try to introduce the many organizations to which I'm affiliated, ENS-REN, the IETR lab, and the sciences team, and also my main research axis. Then I will follow with the different description of different works that I did in collaboration with many other people, of course. The first one on energy management for large-scale EV fleets, AI-based grid modeling for faster security assessment, the integration of dynamic rating in energy management, if I have some time, and also jumping to upcoming project in case that could trigger discussion and collaboration in multi-energy systems and cybersecurity of power systems. So let's try with the introduction. So as I've been introduced, I'm a CNRS researcher in the west of France at the IETR lab. So many different affiliations. We're in the west of France, as you can see. We have a beautiful campus as well, but yours is magnificent, to be honest. So ENS, what does that mean? It means École Normale Supérieure of France, in my case. It's part of the 4 French ENSs, which were with the first one being built right after the French Revolution, and afterwards, more or less, we have one ENS built for every century. So our ENS is the latest, built in 2013. So we're happy to say that we're the ENS of the 21st century. These ENSs, they are accessible through a national contest that is highly competitive and for which students train for 2 years in an intensive training path. Myself, I'm in the mechatronics department of ENS-REN. We have several departments. Our students study mechanical engineering, electrical engineering, physics, etc. And so they have a double degree in mechanical engineering and electrical engineering. And so the perspective of ENS is to train future researchers and lecturers for research and by research. So we have many different projects, research projects that we do during the curriculum. And especially we have, well, our students are self-funded, so that maybe helps to facilitate to send them abroad and anywhere in any place for different types of projects. We have small research projects where they work half a day during 8 weeks in different labs. It could be, well, most of the time located around Rennes for, well, logistical reasons, I would say. But we also have people working at a distance with other labs, which could be in KU Leuven, for instance, most of the time in collaboration with someone around ENS-REN as well. We also have different internship projects coming from 2 to 4 months for the first project to 6 months for a Master 2 level. And we can also have pre-doctoral training where students go abroad or in any kind of lab to start a thesis for 1 year and then embark on a real PhD thesis afterwards. I've talked about sending our students, but your students are also welcome. So we have many different ways of welcoming students. We have the main ENS training path for which there are parallel admissions in parallel to the national contest. We have also master degrees. We have a master in engineering for complex system. We also have another master which we co-manage with Central Supélec, another electrical engineering school in France in smart energy. And of course, we welcome PhD students for short to long stays. So that's for ENS. Now coming to my lab, which is IETR. It stands for Institute for Electronics and Digital Technologies. So we are about 350 members, including 160 PhD and postdocs. Our topics mainly are around energy, security, digital sciences and communications, health, environment, and mobility. So to give you a scale of the lab, on average, we have 40 PhD theses per year, 75 new projects and patents, and 1 startup. And IETR is part of this big umbrella organization that is CNRS, the French National Center for Scientific Research. I'm advertising specifically CNRS here because the national contest for CNRS is starting, well, soon. CNRS offers 100 research position tenured. And that's the applications are done through the submission of a research project, a strong research project. There is fierce competition, and then potentially an audition if you reach the second stage. So as I say, the campaign for offers will open in January, but I would advise anyone who would be interested to join the contest to contact targeted labs well in advance, because we have to build a very strong research project. So it's difficult, but it's very motivating, and it's worth it. So anyone interested, please don't hesitate to contact me if you want. And now maybe to finish, the sciences team that I'm part of. So we do not have a very bad spelling skills in read with sciences written that way. We just managed to find this acronym with ENS right in the middle, so we're very happy of that. We're part of a department that's called Smart Energy. And that's on energy system and sustainable electrical transducers. So we're 5 tenured researchers and 11 if we count the people from the other team of this department, which who are more on control theory for energy. And our main research axes are on the method for the optimal or optimized design and energy management of energy systems, the modeling of these energy systems, whether it be stochastic, multi-physics, etc., eco-design of electrical devices and systems, new concept for actuators and energy conversion, and last but not least, prototyping and digital and analogical validation of all this. This being said, maybe a list of different research activities that I do that I'm interested in. I work in a design and energy management optimization, whether it be large-scale smart grids, microgrids, powered, for instance, from marine renewables, cyber physical systems as well. I'm interested in data centers powered from renewables. I do some modeling tasks on, for instance, the relevant granularity for different models, for different applications. I will talk today a little bit about AI-based modeling for faster security assessment as well. I work as well on the integration of new concepts for the management of electrical networks, whether it be dynamic rating or flexible contract powers, and for upcoming projects, multi-energy systems and cybersecurity. So let's start with the first part on energy management of large-scale EV fleets. So given the audience here, I suppose I do not have to do some background information about the fact that we had to reduce our greenhouse gas emission, etc. We'll have a massive integration of renewables, which means that we'll electrify many different uses, including electrical cars. Of course, integrating renewables leads to many different challenges, including harnessing the variability and uncertainty of these renewables, and the fact that we have to do a paradigm shift to have demand-side management from flexible loads such as electrical vehicles. And energy management, in a nutshell, that is answering the question to when to produce, store, or consume optimally energy. So we'll maybe skip that because you all know that. So we were interested in studying the problem of smart charging in the presence of photovoltaics. For instance, to absorb the excess of photovoltaic power that would happen during noontime. Knowing that each EV owner wants to have its vehicle fully charged or sufficiently charged before departure. That we have also to satisfy grid constraints, avoid congestion, and also satisfy the grid mobility constraints. I say that, and the EV owners also want to minimize its electricity bill. And on the top of that, if we can, we want to add a little bit of fairness. So what is the scale of the problem? We made a very simple calculation based on the Energy Pathway to 2050, which is a perspective document done by the French grid operator RTE. There are different scenarios that are developed by RTE, going from fully renewable to having a more massive share of nuclear. We took, for instance, a moderate, intermediate, I would say, scenario where we have renewables and we also have nuclear. In that scenario, we have about 90 gigawatts of photovoltaics. So what happens when we have a scenario where we are during the summertime and we're at noontime, so there's a peak power production of PV. So we have these 90 gigawatts of installed capacity, but how does it translate into actual production? We took, for instance, the actual production from a day, very sunny day, 2 years ago, where we had about 1.8 gigawatt, I think, of photovoltaic generation, whereas we have about 50.5 gigawatt. We had 50.5 gigawatt of installed capacity at the time. So that gives us a ratio of about 45% of actual production compared to the installed capacity. Let's assume that in 2050, we have bigger PV farms that will be better maintained. They have less shading and whatever. So we can reach maybe a ratio of two-thirds, so 60%. So we apply this ratio to the PV power production. So we get a natural power production of 60 gigawatts. We apply the same rationale to the other energy sources with nuclear, with offshore wind. We assume maybe that's it's a very simplistic scenario, but we do not have onshore wind because it's very sunny. We just have offshore wind, but still it would be a lot of energy. We have hydroelectricity, adding another 5 gigawatts more. And for the load, let's say that we have 20% compared to today's consumption, because we have an increased electrification, we have air conditioning, etc. So we end up with 60 gigawatt of consumption. That leaves us with another production of 45 gigawatts, which translates into about 8 million electrical vehicles charging at 7 kVA. That's these 8 millions, they're about 20% of the cars that are actually at the national level. We have about 38 million cars in France. Of course, we know that not only one actor will have to manage these 8 million vehicles during this peak noon time. But we can reasonably assume that there won't be thousands of aggregators managing all these different electrical vehicles. So the problem that each of them will face is still very large. So there is a problem of scale, and we need decentralized methods. For this, we went to adaptive multi-agent systems, and then we went to bandits, and we combined the two. I will maybe skip the introduction on adaptive multi-agent system. I will do that in EnergyVille, but because it's maybe much more intuitive. Bandits maybe are less intuitive, so I will do a very short introduction, too short introduction, as it said in the slide. But I will do a more detailed presentation in EnergyVille on that tool as well. So I'm very thankful to Raphaël Ferraud, with whom I'm collaborating on this work, for providing me some slides that he had done for the tutorial at the KDD International Conference, and that I've reproduced and adapted. So bandits, where does that weird term comes from? It comes from the one-armed bandits that you can see in casinos. Here in casinos, if you just have one-armed bandit, you just push the arm and you get a reward, and that's it. If you have several bandits like this, you have to choose which one will give you the best reward, actually, if you want to play several times. So that's a multi-armed bandit problem. You will try to sample different bandits and try to guess which one is the best to maximize your reward. So bandits, they are a classical reinforcement learning tool or theoretical framework. And there are parts of this big framework of reinforcement learning, which is divided, I would say, between multi-armed bandits and Markov decision process-based RL, like GQN, PPO, etc., that you may know of. Bandits should be chosen over MDP-based RL method when there is no reason that the optimal policy changes with the played arms. For instance, in Go, if your adversary changed something in the board game, then you have to change your optimal policy. So that cannot be cast as a bandit problem. But here, if there is no reason that the optimal policy changes according to the arm that is played, the decision that you have made, then you should choose bandit. Bandits are very interesting because they are kind of versatile. They can adapt to a wide range of problems. It could be a non-stationary problem. It could be a contextual problem. It could be structured bandit, combinatorial bandit, etc., etc. So when using bandit, when it's possible, instead of MDP-based reinforcement learning. So let's say you have a mold problem in your garden, provided that you take that as a problem. You have two ways of handling that problem. You can use heavy machinery. Well, if you can put that in your garden, well, you have a very big garden. Or you can use very simple tools, and actually bandits are the simple tools. And when a bandit problem can actually be cast in the bandit framework, you can have several gains that you could expect from bandit method. They can be better in cold start, which means that when you have no information about the environment, that the algorithm has to learn everything from the environment, then bandits tends to convert faster than other methods that are based on an MDP. Also, bandits are not very expensive in terms of computational costs, and that's what attracted us because we wanted to have something that is feasible in real-life deployment. So that was one of the key points that was interesting to us at first. And also, bandits could have theoretical guarantees, that is a robustness to unseen problems, which is also attractive because it can contribute in building trust for AI for critical systems, and power systems are critical systems. So here, that's the generic stochastic bandit problem setting. You have a set of arms that are the actions, the decision that you will make. And you have unknown probability distributions and unknown mean rewards for your reward. So for every time step, you would try to choose an action, choose an arm, and then you will wait for the environment to reveal the reward that will follow a given distribution. So that is the generic setting, and each algorithm, each variant will differ in how the player chooses the arm. And there are different algorithms. For instance, the most known one would be the UCB, upper confidence bound, XP3, exponential weight algorithm for exploration and exploitation. You could also have tensor sampling, epsilon greedy, etc. So I will maybe detail a bit more tensor sampling with what we have used. Tensor sampling is based on Bayesian statistic, where you do an assumption of the knowledge that you have on the system. Then when you collect samples through the experiences, and then you update your initial estimation. So here, that's how the algorithm works. At first, you initialize the parameters. Let's say, for instance, that you have a Gaussian distribution, that you have assumed a Gaussian distribution for the environment. You initialize the parameters to a mean value of 0, a sigma variance of 1. And then for each time step, you will sample the estimated value for this reward for each arm, trying to say, well, I estimate that this arm could give me that reward. Of course, it's an estimation, but you will refine that step after step. Ideally, the distribution that you estimate, from which you estimate your sample, from which you sample your estimated value, sorry, should be the conjugate distribution of the actual reward distribution. Once you have your estimated values for the reward, you play an arm, KT, that is the argmax of the reward that you have estimated. And then you observe the reward that is reviewed by the environment following a given distribution that you don't know. And then you can update your estimated distribution low parameters, and then you continue for each time step. You can also use heuristics, maybe not use the conjugate distribution or whatever, or do as you want. There is, in that case, you might lose the theoretical guarantees, but maybe you can fit your problem better. You can have maybe better performances than if you weren't if you were following the I would say the generic setting. And so for our case study, how we applied that to this. The case study is based on an energy community that would have a photovoltaic power. You can see here above the transformer. The community is powered from PV and also from the external grid, for which we have variable prices along the day. We have chosen two scales, one a small scale with 55 EVs, and another one a large scale case study with 10,000 EVs. And the idea is to, well, satisfy all different needs, grid constraints, mobility, etc. Here, for instance, we try to avoid congestion at this transformer here. For the 10,000 case study, we try to avoid the congestion at the 132, 33 kV transformer. And each load that you can see here, each arrow downside, is a district, which is based on the IEEE European Low Voltage Network. So it has 55 load each, and so it reproduced many times to create a big network. So the costs, the objective here is to minimize the daily charging costs of every consumer while ensuring fairness among them, so that the cost for EVs having similar charging patterns wouldn't be that different. We also have to prevent any congestion happening from current and voltage. We have to satisfy the consumer mobility constraints by allowing EVs to have a SOC at departure that is higher than the specified SOC for each consumer. For the power flow constraints, for the bandit-based method, AMS bandit-based method, we use the power system simulator Panda powered. And for the MILP, because we want to use MILP as to give us a lower bound on the cost, we've used a small angle approximation and unit voltage approximation to linearize the power flow constraint that you can see here at the bottom of the slide. Also charging constraints, what the sock within specified range, and the battery dynamic equation in considering the losses. So to identify the problem, we have done sort of physical identification of the problem where each physical component becomes an agent. The line becomes a line agent. It tries to ensure that there is no congestion. The same thing for a bus agent. The PV agent communicates its generation data to EVs, and the EV agent tries to minimize their daily charging costs. So there are two distinct parts in this system. There's the environment, where you have all the reactive agents. There are simple agents, the line, the bus agent, they just transfer information to actually the learning agent, which are the EV agents. And the EV agents, they will learn the quality of their action by looking at the reward obtained from the environment. So regarding the line agent design, a line would calculate its criticality. So criticality is a concept from the AMAS theory that I will not detail here, but it's more or less the distance of an agent from its objective or its constraints. It's a level of dissatisfaction from reaching an objective or a constraint. The criticality here, for instance, for the line agent is 0 when there's no congestion at all. I mean, when it's below a certain threshold. When you reach a certain threshold, then the criticality, is higher, is not 0. It's less than 1, it's higher than 0. And then if you above a certain limit, then it becomes higher than 1. And this criticality, we have added as well a memory term so that we do not have oscillations in the system afterwards. These criticalities are compared by the line to other ones it could receive. It could maybe receive higher criticalities from upper lines, and then it will try to forward that to the EV agent. In our case, we just have used a one-stage propagation model. Regarding the learning agent, so that's a multi-arm bandit come. We try to find the best combination of arms, of actions, that will maximize the reward with all these unknown reward distributions. And the actions are the charging instant, whether you charge or not. So to summarize the EV agent process, each day is divided into M instants that are called the base arms. Each base arm is binary. It's 0, 1, whether you charge or you do not charge, or maybe the reverse, 0 not charging, 1 charging. Each EV picks a combination SKT of charging intervals from the M base arms. It's known as a super arm. And this super arm is the argmax of the vectorial product between the internal features of the super arm times the vector theta, that is the estimated value of the day, of each instant during the day. Each EV charges at selected intervals, and then they will observe the reward from the environment, and then at every time, the estimated reward theta is updated. After a certain time, that might be long or not, you may converge towards the real reward because you do your estimation and you update that every time. And you could do that day after day, and you go back to step 3 for each day. So that's the main framework. You can also do intraday real-time control at each instant, which we have done. You just need here to reduce the amount of time that you just have to reduce the amount of time for charging. So the goal of the EV is to minimize its regrets. The regret is defined as the reward that would have been gained if we were playing the optimal super arm every time, minus the mathematical expectation of what we have actually played. So to summarize, for each day, and then for each instant of the day, the EV will estimate the available free energy before departure. It will calculate the number of grid charging instants required to achieve the desired stock. maybe something I haven't precise. In this particular problem, we have tried to integrate the learning of PV as well. In many other cases, maybe we can take EV forecasting as instance, not being learned by the agent, but given as an input to the EV agent. But that's optional, let's say. Then EV tries to find the estimated best super arm to play, here from a Gaussian distribution. It charges if the current instant selected is in the super arm that was selected. And then it observes the reward from the environment. And here the reward is twofold. If there's no congestion, then the EV doesn't receive any criticality from the environment. So the criticality is equal to 0. Criticality means that there's no the line doesn't see any congestion, the bus agent doesn't see any congestion. So in that case, the reward is 1 minus a normalized cost. That is the cost of electricity during the day. So the lower the cost, the higher the reward. So you will try to charge at the time when energy is cheaper. If, on the contrary, there is a criticality sent to the agent, it means that the criticality here is different from 0, then the criticality is sent as a reward to the agent with a minus sign, which indicates a penalty. Regarding the criticalities, they are sent only to a subset of the agents that are present in the network, and they are sampled from a uniform distribution. So at every instant, you can have different agents being sent these penalties. Then the EV observes the PV energy generation from the PV agent. And then there is an update of the charging strategy for the theta vector I've told you about earlier, plus as an optional a theta vector, a psi vector for PV production forecast. So to come before discussing the results, I just wanted to list the different strategies that we have used to compare the multi-agent system bandit-based method. We have the uncontrolled strategy where no one actually charges during the day. They will just charge at home once they arrive. And well, of course, no surprise, you will see a congestion, right? Then we used MILP to see the lower bound on the cost to give us the theoretical optimum of the problem. Then we have used multi-arm bandit combined with mass without considering PV. They would just have a look at the electricity prices, and then we just add the PV production on the top of that, where they would try to harness PV during the day. So the small case test today is done again, as I said, with 55 EVs. You have a convergence of 30 days, and then we evaluate the performance after these 30 days and during 30 days. So here on the top, you can see the electricity price. It's a normalized price with lower prices during the night and then higher prices during the day. Many different graphs here. Maybe let's first look at this one here with the completely on the right-hand side regarding the constraints. In the two curves that you can, in the two graphs you can see here, they lead to the same conclusion. So let's have a look at the top one, the one in the middle for those who are online. The red curves here shows the uncontrolled strategy. So of course you have this congestion happening because everyone is starting at the same time when you're coming back home. Now, if we look at the strategy where we have the MILP is in green here, you can see that the MILP managed to harness PV production during the day. So there is a feasible solution to harness PV, to have electrical vehicles sufficiently charged before departure and avoiding congestion in the network. Now, our proposed method is in blue here, and it follows very closely the MILP as well. So same thing. We have EV sufficiently charged, avoiding congestion. And then just as an anecdote, I would say we have the other methods that we were studying without considering PV. Well, of course, in that case, that's in orange and yellow here. Of course, they will charge during the times in the day where energy is cheaper. So that is during the night. So that's for the constraint violation, or you can see that we have constraint violated only during the in-control strategy. Regarding the optimality of the solutions, let's have a look here at the top graph. At the top, you can see that you have a green line, which is the MILP, which is a zero cost. And then we look at the percentage of increase compared to that solution for the different solutions that we have investigated. In blue, we have the proposed solution, which is very close to the theoretical solution. And much closer, actually, than the uncontrolled strategy, for instance, where you have very large increase for the cost. And to finish with fairness, we have used this metric for fairness, where D, that's the day, a given day. It's also the set of charging costs for a given day. We have used this matrix here as a one out of many matrices, I would say. For the centralized MIP optimization, we can see that we can have 100% of all EVs charged sufficiently charged before departure, and the fairness index of 1. So there is a feasible solution, and this feasible solution is very closely approached by the bandit AMS-based method, where we have a fairness index of 99%, and also SOC, sufficient SOC before departure for the EVs. So that was the first step, and then we've done the same thing for the large-scale case study, with, again, 10,000 EVs. Again, the same thing. There is convergence after 30 days. There is no consent violation except for the uncontrolled strategy. And here, we can have a look at the costs, reduction of costs compared to other strategies. So in that case, we cannot have the MIP solution. I mean, the problem is far too large. But we can maybe normalize the cost compared to the the highest cost reached in the uncontrolled strategy. So we normalize the cost compared to this peak here. And we can see that, again, the proposed method is much lower than the other strategies here. And for the fairness index, we still have an index of 99%. So the proposed system is, as we wanted it to be, decentralized, able to manage real-time operation. It's scalable, it's near-optimal, model-free, doesn't need to have a model of the electrical network. It's able to tackle stochasticity, and it is fair. So we have the open source code that is shown right here. We're continuing the work as part of a national project that I'm leading. It's called EDEN for Smart Grid. Really love this acronym. It's in collaboration with Orange, EDF, French grid supplier, French energy supplier EDF, and grid operator SRD. We'll have a website advertising all the different news of the project being launched in November this year. We have, plenty of perspective for the work, but here are a few. We want to tackle combinatorial contextual bandits for the future. We're working on that. We are doing the simulation. Unfortunately, I wasn't able to bring some results to you today, but I mean, it's in progress. We want, with this type of bandits, to further reduce the convergence speed and to be able to consider several external conditions, because at the moment, there is one optimal policy that is chosen for all the different days. So weekdays, that would be same. Here we could be able to differentiate between different conditions, let's say weekends, weekdays, etc. We also want to work on theoretical guarantees, and we are also starting something on cybersecurity, and I will tell you more about this at the end of the presentation. So if you're interested, these are the two, I would say, main references that you can have a look at. And then I'll switch to a second topic, which is AI-based grid modeling for faster security assessment. So this work has been done in collaboration with Emmanuel Aldea, which is who is an assistant professor at the SATI lab in Paris-Saclay, University Paris-Saclay. Guy Cabillary, assistant professor at the IRIT lab in University of Toulouse. They're all French. And Juan Cuenca, who's a postdoc. And why I'm advertising that here is because maybe some of you might know Juan, because he's been visiting doctoral students a few years ago, 2 years ago, here in KU Leuven Energyville. And congrats to Juan, he's now assistant professor at IETR, my lab. So we're so happy to have him around. But the other news is that we are hiring, because as Juan is leaving us, but we start continuing working with us on this particular topic of AI-based grid modeling. We have funding that was supposed to be for him, but now it's open to everyone for a 2-year postdoc with a flexible start time. Could be any time between now and April, and with a profile between artificial intelligence and or power systems. So if one of you is interested in applying and has only skills in one of the fields, we can provide training for the other field. But one strong criteria is that we have the applicant must have 18 months outside of France between 2021 and the start time. So now that I've said that, I've done my advertisements, I will try to introduce what that topic is. It's very complementary to what I've presented before. In the first part, I was talking about agent learning from the environment, etc. These agents, they learn, they do AI-based decision making, and based on rewards that are given by the environment. And these rewards, they are, among others, built upon congestion, or the presence or not of congestion. And to define whether there is congestion, we need a power system simulator. What we found is that 86% of the computing time for learning, for training the agent, was taken by power flow simulations and interfacing with a power flow simulator. So we've tried many different things. Reducing the network topology, for instance, we've tried to optimize the code, we've done better memory allocation, we've changed the power system tool from PanaPower to OpenDSS, but still the computing time remains very important, especially because we want to tackle very large-scale problems. So we turn ourselves towards AI-based tools, for which the rationale is very simple. We have consumption and production data. We use a data-driven classification tool, and then we can see whether the network is safe or unsafe, whether there is congestion or not. So to do that, we need a relevant training data set with labelized data, with a network topology, consumption and production data, a power system simulator, and then we end up with labelized data. Yes, but the problem is that we lack time series data for consumption and production. So how can we handle that? In the literature, it's often said that we should have a random strategy with a uniform distribution between a lower bound and an upper bound for the power at each node. So here, for instance, if I were to take this time series data that's from the IEEE low voltage test feeder, we would have an upper bound at around 0, a higher bound at around bit more than 20 kilowatts, and then we would do a random generation, time series generation from this. The problem being that if we do that, most of the operating points generated through this random distribution would be unsafe. So we would have a very unbalanced data set that would be with just a minority class where the network would be safe, which is not representative. Because as you can see, the distribution here for this low voltage network isn't uniform at all. We have low power most of the time, with sometimes a peak, and that's it. So we have to find new methods to generate data for the training datasets. One potential method that we've been using as a baseline, and I will introduce other strategies afterwards, is a modified random strategy, where we keep the same lower bound for the minimum power, 0, and then we apply another limit for the upper bound to get a balanced data set. So that is just a baseline to compare with the other strategies. So the proposed baseline is here. We have another strategy that is a guided single random step, where actually every time we reach a state that is unsafe for the network, we try to reduce the consumption at one node in the electrical network by a random step and once we have found a safe state, then we try to increase again the consumption so that we're always iterating and always exploring the frontier between safe and unsafe state. We do that with just one node. We do the same thing, but with a fixed step. We do a global random step. Here, instead of just picking up one node, we do the same. We increase or decrease the consumption over all the nodes by a random step. For another strategy, we try to do that with multiple exploration, meaning that we pick up we do the same strategy as in B. We try to pick up a node, we try to increase or decrease the consumption by a random step, but here we start with different nodes every time, so we can have different initial points. And we do the same with a fixed step. So these are the different strategies that we have been studying. On the top of these 7 different strategies, we use data augmentation techniques. So these techniques, they help to have a more balanced data set between the minority class and the majority class. if the datasets are very unbalanced, then the classification techniques would fail. So we have to provide some equilibrium between the minority and the majority dataset, but without adding information to the system. And that's what we have done with MOTE. It's a very well-known technique, and it's the graphs here, I mean the drawings, they illustrate that perfectly. We have this majority class here in blue, we have the minority class in green, and SMOT actually creates new samples based on the extrapolation or interpolation of the different nodes that are already existing. And then you get a resampled data set where it's much more balanced, and that will help the classification tools to have better performances. So for the case study, we have used, again, the same IEEE low voltage network, 55 loads. So we have used 55 inputs for the model. We have used different types of models, decision trees, XGBoosts, deep neural network. We also have used several sizing of operating points for the training data sets. So each operating point is a combination of all the different power at each node in the network. So it starts with 1,000 points to 1 million points. We've repeated the process 10 times for each model to have an average of the different runs. And then we apply the 7th strategy plus the other 7 with forced balancing through SMOT. So that leads to a little bit less than 2,000 models. And for the evaluation methodology, what we have done is that, okay, we have trained the model on one of the 7 strategies with or without data augmentation technique. And then we have evaluated the model based on a realistic time series, which is the initial one that I showed you before, which is extracted from the IEEE low voltage test feeder network. So for the training time, we can see decision tree are kind of linear. Well, please note that there is a logarithmic scale here. Decision tree, they have a sort of linear trend here. The sizing, the training time for large-scale data sets, training data sets, being in the order of magnitude as for the deep neural network. The deep neural network having also an increasing training time, but starting is already a significant training time. And XGBoost being somewhat quicker to train. Now looking at the inference, well, the baseline is 7.4 milliseconds of doing a power flow to interface with a power system simulator, OpenDSS, to do the power flow and to give back the value to the rest of the environment. So we can see here that the inference time is much lower for these different tools. Decision trees are way quicker, XGBoost even faster, and deep neural networks, 25 microseconds at least. So there is a huge increase in speed, but what is important is also to be precise. And so we have defined these different metrics for the classification performance. We assume that it's more important to classify, to identify unsafe operational points, as I think you all agree here. I see people nodding. So then, well, if you mistake a safe point as an unsafe point, it's not a big deal. The reverse is a problem. So the precision here is defined as the proportion of correctly predicted unsafe points on all the results classified as unsafe. So the true positive and the false positive. The recall is a proportion of correctly predicted unsafe operational points on all the actually unsafe points, the true positive and the false negative. And so if we look now at the results, so here we have the recall from 0 to 1, the same thing for precision, plus a zoom here for the precision and recall coming from 98% to 100%. What we can see here is that decision trees and XGBoost tools, they actually fail to have decent estimation of the state of the network. Only deep neural networks actually manage to do so, and only for, if you can see the form of the marker here, for very large training sets. So 1 million or a little bit less. And also we can see that the different baselines, sometimes they can achieve very poor results, even for XGBoost. So maybe to do a summary, there is an inadequacy of the conventional techniques for data generation strategies. that we found in literature, especially for low voltage networks where we have this non-uniform distribution of the power levels. We have provided few strategies we have shown with somewhat good performance for a deeper network, but for a very large training data set. And the classification time is reduced by 300, so coming from 7.4 milliseconds to 25 microseconds. But for the perspective of this work, we want to use other techniques, GNN, pins, etc. And we also want, once we have found a very sufficiently good technique, I would say, we want to use deep active learning to reduce the need for data and time. And also we want to tackle the regression problem to have a quantitative assumption of the system state. So this work is also open. I mean, we have the open source code. We're continuing to work on that. And it'll be presented next week for those who will be lucky to go to Dubrovnik in the ITT conference. Again, you can see the different collaborations and a reminder that we're hiring. So I've put many nice postcards of Brittany here if you're interested. It's always sunny in Brittany, right? And so now maybe I can detail the title of the postdoc, which is focused on deep active learning for the AI-based security assessment, and also including AMS and bandits for wind energy. I had done that in the past for photovoltaics, but we want to do that for wind as well. Maybe I have some time to talk about integration of dynamic rating and energy management. Maybe I'll jump to the other two slides because I've been kind of long already. Maybe I'll come back to that if I have some time, but I'd like to leave some time for questions.
Just a question. So this dynamic rating is dynamic line rating.
Actually, dynamic cable rating. We were tackling the inertia of the system, which introduced a lot of problem. But maybe I can. Well, okay. Let's
just explain.
Yeah. No problem. Maybe I'll do that. I'm always too talkative. So, yeah. So dynamic rating was very interesting because I was working initially in wave energy, and wave energy is extremely fluctuating. Here you can see some time series of wave energy production from a simulated wave energy farm, but based on experimental data from a point absorber. And that's highly fluctuating because a point absorber can have a zero power level production and coming up to the maximum power production in a few seconds. It's highly fluctuating. And it's very interesting because the dynamic rating for cables, cables are surrounded, subsea cables are surrounded by the soil, which has a very big thermal inertia, and then you can maybe exploit this inertia to inject far more current into the cable than what is typically allowed under steady state conditions. So that's also applicable to transformers which have also inertia. So we did different work to study different models to integrate dynamic rating for cables, specifically with inertia in energy management. So at first, we had to have a look at the different models. We did some finite element methods to have a benchmark, I mean, the most precise model ever, I would say. Then we tried some RC models, and then we tried some models from standards like the IEC. We've been lucky as well to have partners from the Senref test site in France. It's one of the national test sites for marine energy. So it's located in the west of France. And we had samples from their cable, 20 kV cables, that we have instrumented in the lab, and on which we have done some tests to calibrate a finite element model there. And then we found that we needed, for energy management study, we needed a trade-off between speed and precision, of course, as always. So here we've tried different models. Our model is here, or our final model, I would say, is here, model 2 and 3. There are RC models. And instead of having 27 hours to wait with the FEM model beforehand, we only had 29 minutes to wait for the energy management studies. So that was interesting, especially because the precision was very high. We had about 7% precision minimum in the sense of safety, as it was always overestimating the temperature. And regarding the different studies that we have done for wave energy, we could see that we could possibly inject 2 to 3 times the maximum current of in terms of wave power in the cable than the rating, the constant rating. we could have about 20% more capacity installed without any curtailment. And then we could have more if curtailment is allowed, but then all the economics and the optimal economical point would also depend on the feed-in tariff, etc., and LCOE, on which there is a lot of uncertainty. So difficult to draw any conclusion here on that particular point for the optimal curtailment strategy, but still we consider there is room for improvement for wave energy. Then we have applied that to winds. We wanted to have a look at commitment strategies. In different situations, and in particular in France, we have some very small islands sometimes. They have a very small network, and they have to have more stringent requirement than in the mainland. And sometimes you have to commit, energy producers have to commit their energy, to the commitment on their energy production. And if they deviate from the commitment, they could be penalized. That was one of the call for tender that was applied in France several years ago. And we wanted to see if dynamic rating could have a big impact on the different commitment strategies. So we have compared many different strategies coming from the business as usual, which is based on the P50, the 0.550 based on the forecast, compared to many different other strategies where you can, for instance, have the actual profile. If you're perfect in terms of forecast on your production, how does that translate in terms of revenue? And then an optimal strategy where you do not give your actual production, but actually you play on the imbalance of the network, because sometimes you can be rewarded much more if you sell your electricity at the imbalance price rather than to the day-ahead price. And we can see that when DTR is dynamic thermal rating is included, you can say that for a very extreme case where you have doubled your capacity compared to the cable, you still have a revenue that is more than twice the actual reference revenue, even if you curtail. That means that by playing on the imbalances, you can compensate for the energy losses that you have otherwise. And that is kind of threatening. Well, that's further aggravated, I would say, this behavior. It would be further aggravated by dynamic rating. Regarding now, maybe a last slide on dynamic rating, we wanted as well to integrate dynamic rating into stochastic dynamic programming because it's a well-used tool for energy management, especially for storage. So we've focused on a case study where we have a wind farm, we have storage, and then the problem being that if we have a thermal constraint, then we have to take into account the thermal model. We have to take into account the coupling of the thermal model implied by the thermal model. And if we use stochastic dynamic programming, then the problem is here, the limitation is here that we only had 3 to 5 states to consider. If we go above, then we have an explosion in terms of computing time. So how can we reconciliate the two aspects? We have tried to use a very simple model, a 3-layer RC model that we had discarded in the past for our temperature estimation studies. But we have found that, surprisingly, even though the behavior is not well reproduced, you can see here that at first the RC model reproduces well the near-term behavior, it reproduces well the long-term behavior, but it fails to reproduce accurately the middle-term behavior. We could see that based on different heuristics that we know were optimal, we wanted to have a benchmark. Actually, the stochastic dynamic program with this type of RC model works kind of well. We think it's because it enables to capture the near term and the long term, and it's updated at every instant. So that's maybe how it compensates for this error in the middle part of the horizon. And maybe just few minutes to tell you about upcoming projects. So we are launching a project on multi-energy systems, and specifically on the coupling between biomethane network and electrical network, because they all have, well, both have saturation or congestion in those networks. They all have distributed production or distributed energy resources. And we want to also, investigate the coupling through Carnot batteries that are thermal storage systems. The project itself is called Réseau, for réseau électrique and gas optimisé, so optimization of electrical and gas networks. It's funded by the French gas distribution operator GRDF. It's in collaboration with different entities, the French gas transmission operator, GRT Gas, Kinergy, who's providing a solution for thermal storage based on basalt, a local authority in the Brittany region, another company working in the agro-industrial part. And so for this, we're also hiring, in case you have any Master 2 student who's interested to come to France and we'll have a look at that. We have a flexible starting time, starting in December on. Hopefully we'll recruit someone in that time frame. And the last part, starting with a fun fact on cybersecurity. The fast responding reserves for the power system, there are about 3,000 megawatts all over Europe. And that corresponds to the charge or discharge simultaneously of about 6,000 electrical buses. So that means, in theory, and I put very big quotes, people here online cannot see that, but in theory, you could provoke a blackout on the entire European grid if you hack these 6,000 electrical buses. What's the scale of 6,000 buses? That's actually the number of buses in the Parisian region only. So it's a very small number, after all, when you compare to the entire perimeter of Europe. And also, well, going to less dramatic cases, you can have many different other attack possibilities. So this type of attack could be very interesting to have a look at, especially as we're looking at AI-based control of EV fleets. And that's part of this new project that we're starting anytime soon. We'll have a look at the cyber security challenges of AI-based strategies for controlling EV fleets, potentially EV buses, from electrical buses, and in particular the impact of the power system. So it would be in co-supervision between the ERISA lab and Orange, again, looking at bandits at first, but then expanding to a wider panel of strategies, AI-based strategies, in collaboration with the ERIT lab in Toulouse to look at, again, at AMAS and all that, and in collaboration as well with the University of Manchester to look at the cascading failures in power systems. And a PhD is funded by DNSREN and the China Scholarship Council. And actually, Umar was the catalyzer of all that when you proposed me to integrate a European project that eventually wasn't accepted. But I mean, it was a very nice. Yeah, it was. But he changed. Yeah. And so that's you had a long distance influence as you catalyzed the collaboration between one of my fellow colleagues in Rennes, in the same place, but we always wanted to work together. And then Humar proposed this project and say, okay, we really need to get together and talk about cybersecurity. So we have now this PhD starting, thanks to you. And that will be starting, in November. And I've put that here. And I realized that I'm almost on time, which I wasn't expecting to do. So I must have been talking so fast. I'm so sorry. And that's the end of my presentation. I'll be happy to answer any question you may have.
First part of your presentation. So you mentioned the decentralized charging aspect. So I think the definition of decentralized that you, in the next slide, that you have, same as what we had. And that's because of the control and optimization groups have different definition of decentralized. For us, decentralized means no communication at all.
Okay.
Standalone.
I know.
So I suppose here you mean something like a distributed kind of control. There is some information that you are coming, because for me, capturing the grid constraints without having any communication is very hard. I mean,
it is, and I agree with you. It's distributed in your sense. We had this discussion with the computer scientists with whom we work. I mean, Raphael Faux from Orange is a computer scientist. Guy Camilleri from ERI is a computer scientist as well, and they have the same absence of consensus on distributed and decentralized in their community. And we took their definition from decentralized, which in your case is distributed. So I completely agree. We have communication between. We have here maybe we have communication between the agents, but through the environment. They do not communicate with one another for the EV agent themselves. But I would agree it would fall into the scope of distributed optimization.
And the set points that you calculate is in like day ahead, like or in close to real time. What time scales are we talking about?
It could be both. At first, you can have a day ahead planning strategy where you try to find a super arm for the entire day, and then you can refine day after instant after instant during the day your super arm. You can do both.
So you mentioned something like multi-armed bandits.
Mhm.
So it seems very similar to MDPs because it also has transition probabilities.
Completely. Yeah, it's there are very two different parts for RL. And when you look at the very good book by Sutton and Bartow, they start with multi-agent systems. So it maybe multi-agent systems, I would say they are, sorry, multi-armed bandits. They are the most simple tool for harnessing RL, and then you have more complex tool if you have more complex problems. That cannot be cast as bandit problems.
So what is the key difference you would say from MDP?
Um,
Memorylessness, maybe.
they actually do have memory because they estimate the
MDP
parameters.
is
Mm.
Yes, it only depends on the previous step.
For bandit would do the same actually because you update at every time. But what I understand to be the main difference is that you do not have a change of policy. You can have a change of policy in MDP based RL, whereas in bandit you do not change the policy. Every time you try to update and to converge towards your optimal policy, but you do not change in if you have deviation in your environment.
And the way you implemented it, like maybe the pseudocode was not the exact representation of the implementation. It seems like a brute force. Yeah, this one, like you try to look for all the possible forms.
Yeah, that's and you'll have the answer in energy bill because I will detail that much more. It's too bad I don't have the slide here, but I have a slide that I will show in energy bill where you have the greedy policy. And you can see the record of the greedy policy becoming higher and higher. And then you have the epsilon greedy policy that illustrates this dilemma between exploitation and exploration. Every time when you sample the different arms, you can find best arms and you can try either to go again to the same best arm or try to sample another one that seems less good, but on which you have less information. So maybe it's because you have sampled less.
So this exploration is very similar to dynamic.
Yeah, actually in the book of Sutton and Bartow, you also have a chapter on dynamic programming. So it's all converges, I would say, to the same concept. Yes. Mhm.
But I don't see why the problem that you are solving can be modeled as a multi-arm bandit.
Well, in this for the charging problem, we take super arms, right? And super arms are the charging instant. And then you just have to find a combination of super arm that actually is the best series of 0 and 1 for the problem. And then you just have to choose this combination to get the reward. And then for each day, you try to find the best combination that has to be applied every day. And you update them. Yes, actually, that's why we want to use contextual bandits because at the moment we cannot take let's say a difference density in terms of electrical vehicle present in the network. So we try every time to have an average estimation of how much PV will be produced, how many other EVs might be on the network to estimate the congestion. But we try to reach this optimal policy that doesn't change and to which we will converge in the end. So it's a single optimal policy. Whereas if we use contextual bandit, then we'll be able to say, okay, it's a sunnier day, it's a more cloudy day, we'll have more or less people coming to the lab today and this and so forth. So here we can have different, we can consider the different condition of the environment. But that's not the case for bandits, for the bandits that we have used so far. Maybe that's a good question because we're starting on working on contextual bandit right now. For what I know, and I've asked the expert on bandits on that again. It's really that they do not change the policy. In NDP, you can change the policy. Apparently, I'm not knowledgeable in NDP at all, so you can change the policy. Whereas in bandits, you cannot change that. But maybe I'll ask the question again to the expert to maybe refine my answer. Yep.
And just thinking on the use case, right? So
Mhm.
you have most of the cars, or at least a big chunk of them, charging at night. So, okay, you have information about the PV,
Mhm.
but in any case, you will mostly base your, in this case, your actions on the prices. Because if there is anyway no PV during the night, then you cannot use it.
Yeah.
Right?
Yeah.
So how is that interaction? Or if there is, yeah, some sort of storage there?
Yeah, no, actually, we've used, in the case study, we've used two different behaviors. One where people do not want their EVs to be controlled during the day, so they just plug in when they arrive at home. So that's why they create congestion at home. But if they want they want their EV to be controlled during the day, then they can harness PV. We could have chosen maybe a more, let's say, coherent case study where the EV isn't controlled, but they can still charge in the office. And then we would have a congestion in the office during the day. But it's two two aspects of the case study, I would say.
Yeah, that's interesting because I mean, looking on the charging of electric trucks, and let's say in magnitudes, it's similar to a, let's say, large fleet,
Yeah.
right? And the struggle there is actually the use case, no? So you have a distribution of vehicles that arrive during the day,
Yeah.
nice,
Mhm.
right?
Yeah.
And others that only can be harnessed or, let's say, charged during the night.
Mhm.
And the opportunities for PV are gone
Yeah.
unless you integrate, yeah, storage. And then, yeah, that's the point that I wanted to make with the use case.
Yeah, that is true. In your case study, the perspective is different as the idle time is more during the nights, whereas for EVs, we can reasonably think that during the day there is also reasonable idling time, so we can harness this part of the day as well. Which can. Yeah.
My question is more about the comparison when you were taking the scenario state or unsafe using comparison is the base.
Yeah.
The solve time of OpenDSS was already very minimal, like in milliseconds. So the comparison was also like multiples of that. The figures. I think it's one of the slides where there was like a few.
Yeah, PV boost.
Yeah.
Let me check again. This one. Yeah.
It says the baseline of
Yeah.
7.4 milliseconds.
Yeah.
Of DSS.
Mhm.
And then these would have microseconds improvements. I mean, what is it? The microseconds less than 7.4.
No, actually, that's the total time for inference. When we, it's maybe to put it in other words, we reduce the computing time for powerful simulation by 300, coming from 7 milliseconds for doing a powerful with OpenTSS, including interfacing with OpenTSS. And here, when we use AI-based models, then we just have a computation microseconds.
So that means that then the neural networks take longer than the decision trees.
The deep neural networks, yeah, they take about 20-25 microseconds, and decision trees, yeah, a fraction of microsecond. So they're much slower than decision trees, but then we have seen that the performance in terms of classification is much higher.
But for the problem of security assessment, is the 7.4 microseconds too long for that problem?
I see what you mean. Yeah.
Maybe if OpenDSS will do an actual power flow and then give me true values without the margin of error, while these models might have a margin of error.
I completely get your point, and I didn't mention that we want to use these models to accelerate the training of the AI-based agents, and we want to use that for simulation. We do not want to use this tool for actual security assessment by a DSO. We want to use this as an accelerator for our studies on AI-based management. And if we can get something that is sufficiently precise, but far quicker, that would be interesting, because for simulating 10,000 agents for 2 months, it took us 1 week. So that reduces the amount of studies that you can make. So we want just to accelerate the time to have more, or to be able to produce more studies. Yeah, the 55, and that's only for 55 loads. So going larger, that's why we see the need for deep active learning.
So why do you plot like the size of training set on the x-axis? Because why is it a function of the operational time? Because this is the test time, right?
So yeah, the operational time is the inference time. And the training dataset size, well, because actually we wanted to have a look at the increase of the operational time as a function of the different scenarios. We've done that, actually, we've done that for the training time. We wanted to have the same graph for the operational time, that's all. There's no, for deep neural networks, there's no influence. We can see some sort of influence potentially, but very, very small for decision trees, not so much for XGBoosts.
And the accuracy is like very high.
Not really, not really. It depends what you consider as high. We took the assumption that if we have to assess with a very precise way for critical systems, we have to be between 99% and 100% of recall and precision. And we could see that for decision trees and XGBoosts, they do not achieve this performance, even for very large training data sets. Only deep neural networks can do that. And for mostly the strategy that we have presented, that is F or F plus mod, ND and D plus mod. So 2 strategies plus their counterpart with data augmentation techniques. But for the rest, we can see that, well, okay, we can manage to have something that is more or less nice, but maybe not sufficient here, as it's very poor for decision trees and we're in the middle for XGBoosts.
So we are also pursuing like the PIN, I think you already know that. So we have a PhD and a few master theses in that, trying to develop an ACPF model, machine learning plus the physics, not losing it.
Yep. Yeah, and I've seen the paper, it's very interesting. We can talk more about this.
Improving on it.
You say you're using this to train your agents.
Yep.
But then say that your strategy gets implemented in industry, actual setting where you're not so much looking at what are the best parameters. Would you then still go for something like this where you use a deep neural network to approximate your flow? Or do you think like, okay, you only need to train it once, might as well use OpenDSS to get the maximum safety?
Yeah, actually, we discussed with Grid Operator RCRD on this. They didn't show so much interest in having a power security assessment based on artificial intelligence, because, as you say, power flow are sufficient. The reconfiguration, there aren't so many configuration available, so that's why we want to restrict the use of this tool only for the training of AI-based energy management strategies, because there's a lot of iteration that we need to train the model for the AI-based management strategies. So that's why we want to accelerate every second that is saved for the power system. The power flow simulation is saved for training the agent. Right? Any questions online?
Yes.
Okay. It's been so clear. Thanks very much for attending. I'm happy to discuss.
Better to take a picture. Maybe you can have the first slide.
Yeah.
The initial slide in which the lab name.
And still, I'll have to get my pointer back. Always changing after this one.
Yep.
It's about to this problem. I guess you can
Yeah.
It's enough proof I am.
Okay. Yeah, we like to give our speakers some goodies. So this one is essentially a cursor for the market. If you wanted to use this for your passport, then even much. So yeah.
Thanks. Thank you so much. Thanks very much.
Maybe.
Yeah. You want to come over as well?
Maybe
Yeah. No.
should not have to be put.
Thank you so much.
Okay, yeah, sure.
And you send it to me afterwards?
Yeah. Yeah, it's.
Yeah.
Yeah, thanks everyone for attending.
Thanks, everyone.